In this video, we're going to go over Chapter 4, Naming Alkenes. So there's a difference between naming alkanes and alkenes. For alkanes, or the C single bond is an alkane, and the suffix is -ane. For alkenes, it's a double bond, is an alkene, and the suffix is equal to -ene. So just like it has in the name, -ene versus -ane. So if you look at butane, we have 1, 2, 3, 4 carbons. This is butane and an alkane. The alkene version of it would have a double bond. We'll put it on the first carbon. And now this is 1, 2, 3, 4, be 1 butene. If we have another example, if we have pentane, this is pentane, and this would be 1 pentene. So numbering the parent carbon chain in alkenes is a little different than alkanes. You always look for the longest, you should look for the longest carbon chain, but it has to include the carbon double bond in the parent chain. And we want the smallest number for the first carbon. So for that carbon 1 in the double bond, that you can, because we want to make sure it's just the closest to the end as we can. So let's do an example. We have this molecule here. And if we count, we can either do 1, 2, 3, 4, 5, 6 carbons this way, or we can do 1, 2, 3, 4, 5, 6 carbons the other way. This way, the double bond is a carbon 1 and carbon 2. This way, it's carbon 5 and carbon 6. So we want the smallest number to be the double carbon bond. So this method is what we want. We're not going to do the bottom. So to name this, we have 6 carbons, which is equal to hexene. We have a methyl on carbon 4, and our double bond is on C1 and C2. And so it starts on C1, so the name would be 1, would have this 1 in front. So it would be 4-methyl, you do the substituents first, 1-hexene. That would be the name for that molecule. We could do another one where we have this molecule. We can number it either from the left, 1, 2, 3, 4, 5, or we can do it from the right. We have 1, 2, 3, 4, 5. This way, our double bond is 3 and 4. Going from right to left, our double bond is 2 and 3. So this is the way we want. We don't want the top because the numbers aren't as big or too big. We want the carbon-carbon double bond to be on the lowest number it can. So this would be, and we do from the first carbon, it'd be 2 pentene. Another example would be this molecule. Now this molecule, we want to do the carbon chain. So we have 1, 2, 3, 4, 5, 6 carbons this way, but it doesn't have the carbon-carbon double bond in it. So we can't just go across the zigzag. We have to include this double bond. So this way we have 1, 2, 3, 4, 5. Oops, sorry, I counted that one twice. So it'd be 1, 2, 3, 4, 5. So even though this is a 5-carbon chain and just straight across the zigzag is 6 carbons, and that's longer, we still need to have that carbon-carbon double bond in it. So we can't, that one wouldn't be correct. And we have our carbon double bond on C1 and C2, so that's as close as it can. And it's 5 carbons, so it would be 1 pentene. On carbon 3, we have a methyl. And on carbon 2, we have an ethyl. So E comes before M, so it'd be 2 ethyl, 3 methyl, 1 pentene. So that would be the name of this molecule. So now we want to draw the structural formula for this compound. We have a 2,3-dimethyl 2-butene. So the first thing we're going to do is draw out our 4-carbon chain. We have 1, 2, 3, 4. We have the carbon-carbon double bond on 2 is where it starts. So it's 2, 3. And then dimethyl, we have 1 on 2 and 1 on 3. So we have 1 on 2 and 1 on 3. So that is 2,3-dimethyl 2-butene. Next one, we want to know what's wrong with this name, 1-methylpropene. So we're going to draw our 3-carbon chain because propene is 3. We have a methyl on 1. And we would have our carbon double bond on 1 as well. So we have, this is 1, 2, 3. But if we look at it, it is actually a 4-carbon chain because this is 1 now too. So it'd be 1, 2, 3, 4. So this would actually be 2-butene. Because 4 carbons means but, and you have the 2 to the 3, so it starts on the 2. Cis-trans isomerism. So cis-trans, you can have cis-trans or EZ for alkenes. So if we look at a molecule like this, we have it numbered 1, 2, 3, 4, 5. We would look at the substituents coming off of the double bond. So we have one here, and carbon-carbon double bonds always have 4 things coming off it. We just don't show the hydrogens. So we're going to show the hydrogens now. H, H. You can see that the H's are on the same side as the same part of the plane. So if you think of a plane across the bond, the H's are on the top, the 2 carbon substituents are on the bottom. So they're both in the same plane. Carbon and carbons are on the same plane, hydrogens and hydrogens are on the same plane. So that means it's a cis. If we have this version of it, so it's the same thing. It's a 1, 2, 3, 4, 5. We have there's a methyl on carbon 4, and the double bond is on the second carbon. This one will do an H that side, H on the other side to show them. And if you look at the plane, the H's are on opposite sides of each other. So this is trans. Trans means different sides. Cis means same side. Now EZ is different. EZ assigns priorities to the substituents coming off a double bond. And there's a couple rules for this that we'll go over, but this is used for tri and tetra substituted alkenes. So you can't do cis and trans for, so this is a 3 and a 4 substituted alkenes. Only easy. So if we look at a double bond, this, say we have, so it assigns a priority each side of the double bond. So you'll have a higher priority and a lower priority on each carbon of the double bond. So let's say the higher priority is up here and the lower priority group is down here. Again, higher is on top, lower is on bottom. You put your plane through the bond. You have higher, higher on top, and lower on bottom. So if this would look like a cis because the higher and higher on the same side, but because it would have 3 or 4 substituents on it, we cannot use cis and trans. So Z is equal to this, oops, same side. The higher priority is on the same side. Then if we did it this way, so we have the higher on the top, lower on the bottom, but then we have the lower on the top on the second carbon and higher priority on the bottom on the second carbon. We draw our plane. Higher is on the top and the bottom. They're different. So it's going to be E. The higher priority groups are on opposite sides. One way to remember this that I saw, which I think is a bit funny, is Z is the same side. Z same side. It's funny. And then for E, you can say it's the E posit. Instead of opposite, it's E posit. You can say it however you want, whatever you think will help you understand it and remember it, but that's just what I saw somewhere that I thought was helpful. Okay, so this one we want to see which one can exist as easy isomers. So first we're going to draw it out. So C carbons, we have two H's on the first carbon. We have an H and a Br on the second. H's, two H's on one side, these are the same. So you can't have lower or higher priority because they're going to be exactly the same. So this one cannot have easy. This one, let's write it out. So we have an H on one side, CH3 on the other, and an H and a Br on the other. These two on the first carbon are different. The ones on the second carbon are different than each other. So yes, you can have easy isomerism exists with this one. So for easy isomers, priority rule number one is that the higher atomic number equals the higher priority. Remember this. Remember, the atomic number is the number of protons. So hydrogen would be atomic number equals 1. Helium would equal 2, and so forth. So we can do an example here. We're just going to have our basic carbon double bond like we did before. Let's have an iodine, an amine, or amino, a methyl, and a hydrogen. So we're going to look at carbon 1 first. We have iodine and nitrogen, or amino. Iodine's atomic number is equal to 53. Nitrogen's atomic number is 7. We look at the atom directly bonded to the double bond carbon. Look at atom directly bonded to carbon in the carbon-carbon double bond. So that means we're looking at nitrogen and iodine. Iodine has the higher atomic number, so therefore it is higher priority. If we look on the other side, we have carbon and hydrogen, which is equal to 1. Carbon is 6. Carbon is higher than hydrogen, so this is our higher priority. The higher priorities are on the same side of the plane. Oops, no. So this would be Z. Because remember, higher on the same side versus lower is the Z. So higher is Z. Now, if we have this molecule with a HCH3, Cl, and bromine, we look at carbon number 1, where we have bromine and chlorine. Bromine is atomic number 35. Chlorine is atomic number 17. Bromine has a higher atomic number, so bromine is higher priority. On this carbon, we have carbon from our CH3 and a hydrogen. Carbon is atomic number 6. Hydrogen is atomic number 1. Therefore, the CH3 is the higher priority, and so this is Z again. Priority number 2, or priority rule number 2, if you can't assign priority when looking at the first atom on the double bond, then you look at the second one, and so on. So that would be, if you can't assign priority, then that means that the first atoms bonded to the carbon on carbon are the same. So then you look at the second ones, if those are the same, then you go on to third ones and so forth. You look until you see the first point of difference. Between the two groups. And you still go off of the atomic number to assign priority. So for example, we have this double bond, carbon 1 has a CH2Cl group on it. Bottom has a CH3. Carbon number 2 has a CH3 group coming off the top and a CH2CH3 group. So the first thing we're going to do is look at how they are structured. So you may look and see C is bonded to H2, this is C bonded to H. What you're going to do is look at the actual structure of it. So C is bonded to ClH. Bonded to C, double bonded to carbon. This one is C, hydrogen, hydrogen, hydrogen. Then on the other side, it's carbon, hydrogen, hydrogen, hydrogen. And then we have CH2 group bonded to a CH3. So if we look on this side, our atom directly bonded to the double bond is carbon. Right here and carbon over here. They're the same. So now we go on the second atom. We go across the line. So our second atom is chlorine. So we're comparing chlorine to hydrogen because this is 1, 2. Chlorine has a higher atomic number than hydrogen, so this is higher priority. We look on this side, we have a carbon bonded to a hydrogen, and then this carbon bonded to another carbon. Carbon is higher priority than hydrogen. So this one is the higher priority. They are on opposite sides, which makes it E isomer. We can do another example here. If you're given a molecule that looks like this, we have a chlorine on this side, our double bond, a methyl group, and a methyl group, and then CH2. or CH2, CH3 on there. The first thing that I do that I find helpful is to draw everything out based off of this double bond. So let's say this is carbon 1, carbon 2. We have carbon 1 and carbon 2. Carbon 1 pointing down is a methyl group. The part pointing up is a CH2Cl group. On the other carbon, you have a methyl pointing up, and you have an ethyl. So this is up, up, down, down. You have an ethyl, which is CH2, CH3. And like we said in the last one, we are comparing, we already know that carbons are the same, so we're going to cross those out. Our next one is we're going to compare hydrogen to chlorine. Chlorine is greater than hydrogen, so that's higher priority. In this one, our carbons are the same. Now we're going to look at carbon versus hydrogen, because remember, this is carbon bonded to carbon, and the H's are off to the side. So we're looking at this interaction. Carbon is higher than hydrogen, so this is higher priority. They're on opposite sides, so that means that it is an E conformation. Okay, so this is the same molecule. And we already specified that it's E, and this is how we include it in the name. So we're going to number it, and we have 1, so we could have 1, 2, 3, 4 carbons, and carbon would be, the double bond would be on 2. Or we can number it 1, 2, 3, 4, 5. That has higher carbon chain, so that's good. The carbon-carbon double bond is on 3 and 4. If we number it the other way, we have 1, 2, 3, 4, 5. We have our carbon-carbon double bond on the 2 and the 3, so that's the one we want to do. So this one, we have 5 carbon double bond, or alkene, so that's going to mean it's a pentene. The carbon double bond starts on, it's at C2 and C3, which means that it's a 2-pentene. We have methyl groups on 2 and 3, so we have a 2-methyl and a 3-methyl, which goes to 2,3-dimethyl. And off of carbon 1, we have a chloro group. So it's 1-chloro. So the name of this one would be, because chloro comes before M, C comes before M, be 1-chloro, 2,3-dimethyl, 2-pentene. But we forgot the E and Z. So where do those go? Goes, where is it? Right here. E goes in the front in parentheses.